Good morning, students. Today I am taking one topic of Unit 5th, State Space Analysis of Control System. In earlier topics, the analysis of control system is carried out based on transfer functions and graphical methods such as root locus, Nyquist, transfer function, root locus, Nyquist plot, etc. Transfer function shows the input-output relationships. The earlier methods are used for static systems only. These methods are used for the static system only, in which we consider that the initial conditions are zero. But if we talk about the dynamic system, that is in actual systems, the initial conditions may be present with input. So, transfer function, root locus, Nyquist plot, Bode plot, etc. all are talking about the static system. And if we talk about the dynamic system, we have to move to state space analysis. So in static systems, the initial conditions were zero. We were taken initial conditions are equal to zero. In the dynamic system, the initial conditions are present if input is given. If some input is given, obviously input will be given to the system, but to that system initial conditions may be present. So that system is called dynamic system, and for the analysis of dynamic system, state space analysis is required. Now if I am taking an example of dynamic system, if I am talking about the operational amplifier, in the operational amplifier, if input is not given, but the output offset voltage is present without giving any input, this output offset voltage is actually the initial conditions when input is given. So when input is provided to the operational amplifier, the output will not be desirable due to the presence of the offset voltage. Therefore, it is required to consider the initial conditions with input so that we can got the correct result. So in a state space method, input and initial conditions both will be considered. Method input plus initial conditions will be considered. So, but when we start state space, the initial conditions are kept zero. Slowly, once we accommodate with this method, initial conditions will be included with input. So now I am starting state space representation. How the system can be represented in the form of state space. So I am considering a system or any system can be explained through the differential equations. Any system can be explained through the differential equations Consider second order differential equation. Let d square x upon dt square plus b d square xt upon dt plus cx equal to u. Now, for the state space representation, this is required that the initial conditions keep equal to 0. So I'm consider here the value of xt is equal to 0 at time t equal to 0, and obviously the differentiation of this will also be equal to 0. So the initial conditions are taken equal to 0. If I am taking initial conditions equal to 0, then Laplace transform of this will be represented by as x of s. Okay, now rearrange the equation and keep the highest order differential form and move all the terms to the right hand side. Right hand side. So equation is what we wrote for the equation: d square upon dt square plus b dx upon dt plus c xt equal to ut. This we considered. It means what we have to do for the state space representation: keep the highest order differential term on the left hand side and move all these terms to the right hand side. So I am writing here minus bxt upon dt So you can see here the highest differential term is written on the left hand side and all other terms are moved to the right hand side. Now this is important to listen. Let I am considering the xt, let it be equal to x1. Let this be equal to x1. Now if I am taking the differentiation of this, so this will be represented by x1 dot. Differentiation is always represented by the dot. If this is double differentiation, it can be represented by double dot. But now here this is single differentiation, so this is represented by x1 dot. Since xt is equal to x1, here I am taking the differentiation of this. So to show the differentiation of this, I can represent like this: x1 dot. Now let it be equal to x2. Okay, now next I am taking double differentiation of this input xt. So this is equal to x1 double dot or x2 dot. Now this is equal to x2 dot. हम हमेशा कहाँ तक डिफरेंशिएशन का कंसिडर करेंगे? जहाँ तक हमारे पास हाईएस्ट डिफरेंशियल होगा. हमारे पास जैसे ये इक्वेशन है, इस इक्वेशन में हाईएस्ट डिफरेंशिएशन कहाँ है? डी स्क्वायर है, तो मैंने डी स्क्वायर तक इसको कंसिडर कर लिया. नाउ पुट ऑल दीज वैल्यूज इन दिस इक्वेशन. सो आई एम पुटिंग डी स्क्वायर एक्स टी अपॉन डी टी स्क्वायर इक्वल टू x2 dot. I am writing here x2 dot. Now there is one more thing to be considered here कि हम जब भी लेफ्ट हैंड साइड पे लिखेंगे जो भी टर्म, उसको हम डॉट के फॉर्म में लिखेंगे, डिफरेंशिएशन के फॉर्म में. और जब हम राइट हैंड साइड पे लिखेंगे वो विदाउट डॉट लिखेंगे, मतलब बिना डिफरेंशिएशन के लिखना है हमें. सो आई एम राइटिंग हियर दिस ut as it is minus b. Now here dxt upon dt, you can see here dxt upon dt is equal to x1 dot, but on the right hand side don't write this. This is equal to x2 also. We have considered x1 dot is equal to x2, so I will write this term x2. Next c, I am writing here as it is. This xt is considered as x1, so I am writing here it is equal to x1. So this equation is written like this. Now in this equation you can see on the left hand side I have taken the term with dot, and on the right hand side I have taken the terms without any dot. So this is important. Now this is the one equation. This is equation number 2 actually, since we have already write first equation x1 dot is equal to x2. This is first equation number 1. We have considered this x1 dot equal to x2, and now x2 dot is equal to this much. Now these two equations describes the dynamics of the system.